All right, so day 2 of section 2.4. So yesterday we talked about optimizing area in certain quadratic relationships. And now we're going to move into optimizing volume in cubic relationships. And we're going to do it using volume. Remember, volume is area of the base times the height of a three-dimensional object. Length times width times height is, how it's usually expressed in elementary and middle school. So in this question it says, so you have to understand the question. I'm going to take a moment to make sure you understand it, and then we'll get into it. So squares with sides of length x are cut from the corners of a rectangular sheet of paper, which you can see here. This is your rectangle right here, okay? So you're basically cutting these squares out, right? The squares have length x. Okay, so they're cut from the corners of a rectangular piece of sheet metal with dimensions 6 by 10. So the entire sheet is 6 by 10. The metal is then folded up to make an open top box. What's the maximum volume of the box? All right, so to kind of help you with this, I'm going to show you a visual real quick that should help you kind of process what's actually happening here. So on the left side, you can kind of see the purple area. So the entire shape, that entire rectangle, is the piece of sheet metal, which in that example the previous example was 6 by 10. And then we have these squares we're cutting out, and you can see them in red here, right? So you have these 4 squares that we're going to remove. And then what we're going to do is we're going to fold it along the edges and create a box, right? So, and you can do this, you can change the size of the squares you remove out of this object. And that's kind of what we're going to investigate today. And then we're going to look at the box. So let's just show you what it looks like. So when we fold it, that's the what's going to be happening, right? So we're cutting those 4 squares out, and then we're going to fold it up. And now we have a 3-dimensional box without a lid, and we're going to calculate the volume of that, right? So that's the first piece of understanding is, right? And the goal is, what size square over here, right, as we look at it, right? What size square can we actually remove to optimize our volume, right? Because there's different sizes there, right? So that's ultimately where we're getting into. So this is also a problem I do in a geometry class. We're not going to do it the same way, but okay. So the question is, first you have to kind of make sense of dimensions, right? So the entire dimension is 6 by 10, as you can see. But if we're cutting out, these squares right here, what we're doing, if you just focus on the top of this rectangle right now, I'm removing this x and the other x on the right here from that top dimension, which did measure 10. So if I take this x off and then I take this x off of that, then what I'm really doing is I'm subtracting 2x from that dimension of 10. And the same thing on the other dimension right here, right? So I'm taking this x off of that side, and I'm also taking this x off of that side, and the original side was 6, so I'm really subtracting 2x from that dimension of 6, right? So now if I remove the x's and kind of folded the sides to make a box, this is essentially the 3-dimensional shape that we're looking at, where in the red here, that dimension is going to measure 10 minus 2x for the 2 squares you cut off of that side. And then on the other side here, that's going to be 6 minus 2x for the 2 squares you cut off of, that side, right? And then the height of the box here is x, right? That's this height right here. Whoops, excuse that. What's going on there? How do I get out of here? Cancel. So this x here, right, is essentially the size of the square you cut off, right? Okay, so now volume is base times height, or area of the base times height, right? Or length times width times height, however you want to visualize it. But it's basically this dimension times that dimension, right? So when I express that in a volume function here, this is essentially a cubic polynomial, right? I have one factor times another factor times another factor, so that's going to give me an x cubed polynomial. So what's nice about this problem is it's in factored form already. Now this isn't completely factored, but it's factored enough to allow us to find zeros of the function, right? So if I use the zero product property and set this factor equal to 0 and solve, I end up with a 0 of 0. If I use this factor and set it equal to 0 and solve, I end up with a factor of positive 3. If I set this factor equal to 0 and solve, I end up with a factor of 5. Those are my 3 zeros, right? So now what we're going to do is kind of express that on a graph to visualize it, right? This is just a sketch, it's not perfect. So what I did was I set up my coordinate system and then I dropped my 3 zeros in. One at x equals 0, one at x equals 3, and one at x equals 5 here, right? It's cubic, and if you kind of look at this situation, you can't really see it from this function alone, but if you were to distribute everything here, eventually you're going to multiply this green x to this negative 2x in blue to this negative 2x in red. Right? So just the product from here to here is going to give us a positive 4x squared. And then when I multiply that positive 4x squared to this green x there, that's going to give me a positive 4x cubed now, right? So you could look at this as 4x cubed, and then there's going to be some terms in the middle, and then your constant here, right, is going to be 0. And you know, you can't see it right from here, but eventually you're going to be multiplying this 6 to that 10, which is 60, but this green factor here, right, that's really x minus 0, so you're going to be multiplying this 0 to this 6 and to that 10, which is going to give you 0, right? So my y-intercept is 0, which is going to correlate nicely with that piece. But more importantly here, what I wanted to know was, you know, what's the sign of my leading coefficient? It's positive 4x cubed. So I know that from this point here, my graph is going to run up, and then it's going to turn back down to this blue 0 down here, and then it's going to turn back up to this green, right? So understanding the graph itself, this section of the graph right here is irrelevant in the context, because if you think about it, the y-axis here is volume, right? So this red section of the curve down here that would indicate a negative volume, and in this situation that makes no sense, okay? Also, anything past this green or this blue point 3, right? So remember, the x here is that's the length of the little square we cut off of that big piece of paper, right? If you go back to it, right? And it goes on, and it just, you know, right? So that's what the x is in this function right now, right? So it also makes sense that this red piece isn't here, because anything larger than 3, right, units here, would mean I'm cutting off a square here, you know, that's 3 units on this side and then 3 units on this side, right? So that would be a square like this, and then another square like this. But you can't really do that, because if you cut this whole square out and then you cut this whole square out, you have nothing left on that side, right? So anything larger than 3 units right now is going to not allow us to create this box, okay? So ultimately our goal is to pretty much find the maximum volume, and that maximum volume is going to show up right here, all right? Remember, this is an approximation. Calculus will allow you to find the maximum volume when you take that course, but for now what we're doing is we're taking this 0 in green, this 0 in blue, we're finding the average, the midpoint, which is 1.5, and then we're going to take that 1.5 and plug it back into our volume function, right? So remember, volume of x is x times 6 minus 2x times 10 minus 2x here. So when I plug that in, right, we're going to have a 1.5 for x, 6 minus 2 times 1.5, or, you know, 3 halves, and then 10 minus 2 times 1.5 here, right? So you're going to go through and do the math for that problem. Take your time, be methodical. I'm going to do it right now. So 1.5 times 6 minus 1.5 times 10 minus 2 times 1.5 is 31.5. So this gives me a total volume of 31.5. I'm not sure what the units are. Let's look at the units, inches. So this would be inches cubed here, right? So a square so a square of 1.5 inches will produce a maximum volume of 31.5 inches cubed. Let's go back up and check our max. What is the maximum volume of such a box? All right, so we kind of hit all those pieces there.